This is video 2 for chapter 19. In this video, we're going to learn about Gibbs free energy, which has this symbol G. You learned in the previous video that G is a thermodynamic term or quantity, and what we use this one to determine is whether or not a reaction is spontaneous at that given temperature. So here's how this breaks down. If the delta G value is negative, then our forward reaction is spontaneous. It will happen at that set of temperature spontaneously, which means just without intervention. If delta G equals 0, the reaction is at equilibrium. And if delta G is greater than 0 or positive, then the forward reaction is not spontaneous, but the reverse reaction would be. So remember, we're always talking about the reaction as written. And you can look at the sign of delta G to determine whether a reaction would be spontaneous or not. Now, delta G for a reaction is calculated the exact same way that the other two thermodynamic quantities we've talked about are calculated. So if you remember with delta H and S, we calculate them by doing the sum of the products minus the sum of the reactants. And again, all of these values are found in Appendix C in your textbook. Now the units of G are in kilojoules per mole, just like the units of delta H. And just like with delta H, if you remember way back to chapter 5, if you have an element in its standard state, for example, O2 gas, that will have a delta H value of 0, and it also will have a free energy of 0. Another example would be aluminum solid. Both the delta H values and the Gibbs free energy, delta G values, would be 0. So how do we do this math? We'll just do a quick example problem. In this example, it's giving you a reaction and it says to calculate the standard free energy change for the reaction that's shown, and then it asks you to determine if that reaction is spontaneous or non-spontaneous. So you're going to want to go into Appendix C, and you want to be really careful that you use the right column of values, okay? So the first thing we're going to do is figure out what the products will be. So I'm going to make a little list here just because there's a lot more elements and compounds here. So for silver, at its standard state, that has a value assigned to it of 0. So even though there's 4 moles of silver, and I'm writing down all of this to be obvious, this has a value of 0 kilojoules per mole. Now that's the part that is just the silver. I have to add to it the sum of all these other reactants. So I'm going to look up the value of H2S, and that has a delta G value of negative 33.01 kilojoules per mole. And in this balanced reaction, there are 2 moles of it formed. And then my last product is oxygen. Again, gas at standard state would have a value of 0 kilojoules per mole. And I'm going to multiply by the 1 mole. So the bottom line is, for the products, I get a total of negative 66.2 kilojoules. That's my delta G for my products. I'm going to do the same thing now for the reactants. So looking at the silver sulfide. Now this one right here, silver sulfide, that one is not in your textbook. I found it at a different textbook. So you just have to take my word for this one. You have a value of negative 40.7 kilojoules per mole. And we're going to multiply that one by 2 moles because of the coefficient of 2. And then I'm going to add to that the value for water. Now water, if we look that up, has a value of negative 237.13 kilojoules per mole. And again, in this balanced chemical reaction, there are 2 moles. So when I do this math, for the reactants, I get a total, when I sum these, I get a total of, let's see, I didn't actually give myself a total, so we'll quickly add those. Oops, here. you should get a total of negative 555.66 kilojoules. Now remember, we're not finished until we actually do the subtraction. So products minus reactants. And we want to make sure we're careful with our significant digits. Just kind of think of this as adding our problems together. So when we add, we want to make sure we count our decimal places. So you should come up with a positive 489 point. And now since there are 2 decimal places in my calculator, I get 46. I'm going to actually round that to 1 decimal place because that has one decimal place. So 489.5, and then the label would be in kilojoules. And so that is my delta G value for this particular problem. And the question says, is this reaction spontaneous or non-spontaneous? So we can see that it's a positive answer. So we go back up to our notes, and we see that when delta G is positive, the forward reaction as written is non-spontaneous. And that is how you calculate Gibbs free energy using appendix C values. Just exactly the same way you would have calculated delta H in chapter 5 and delta S that you learned how to do recently.